At some point in the future, so distant that the human mind can barely imagine, everything we know will cease to exist. The stars that now twinkle in the night sky will go out one by one until not a single point of light remains. The planets, including Earth, will vanish. Their structures will be dismantled atom by atom, and even the particles that make up your body will not escape the relentless passage of cosmic time. The universe, despite its vastness and grandeur, carries an expiration date written in the laws of physics, and at the center of this story is an unlikely protagonist, the proton. Before we dive into this journey through the fate of the cosmos, take a moment to subscribe to the channel and hit the like button. This helps us keep bringing you content that explores the greatest mysteries of the universe. Now, to understand the role of this particle, we must go back more than a century to the beginning of a scientific revolution. In the late 19th century, classical physics seemed solid, almost complete. Many scientists believed we had already deciphered the main laws of nature. The prevailing idea was that matter was made of indivisible atoms, eternal, unchanging. A concept inherited from Greek philosophers, preserved almost untouched for centuries. But in 1897, J.J. Thomson changed everything. In experiments with cathode rays, he observed unusual deviations in the beam and realized he had discovered something new: the electron. This discovery was a shock, revealing that the atom was not indivisible, but had an internal structure. Thomson proposed the plum pudding model, with electrons embedded in a positive sphere, and although it was imperfect, it opened the door to a new physics. From then on, scientists around the world raced to explore the depths of the atom, ushering in an era of discoveries that would forever change our view of reality. In 1911, Ernest Rutherford conducted one of the most elegant and surprising experiments in history. He used alpha particles to bombard an extremely thin sheet of gold, only a few atoms thick. According to Thomson's model, all the particles should have passed through with minimal deviation. But, to Rutherford's astonishment, some bounced almost directly back. It was like firing a bullet at a sheet of paper and having it return. The only possible explanation was the existence of an extremely small, dense, positively charged nucleus. A few years later, Rutherford identified the proton as an essential component of this nucleus, laying the foundations of modern nuclear physics. This finding not only rewrote the structure of the atom, but gave us the particle now seen as a candidate for determining the fate of the universe. For decades, protons and neutrons were treated as fundamental particles, but with the advancement of particle accelerators, in the second half of the 20th century came a new revelation. They are made of quarks. There are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. However, only 2, up and down, form all ordinary matter. In the proton, 2 up quarks and 1 down quark bind together. In the neutron, it's 2 down quarks and 1 up. These quarks are held together by the strong nuclear force, mediated by gluons, and this bond is so powerful that separating 2 quarks is impossible without creating new ones in the process. This discovery not only redefined what is fundamental, but also showed that the stability of matter depends on interactions at almost unimaginable energy scales. And this raises a deep question. If even the building blocks of the proton can, in theory, change, what stops it from disappearing over time? Matter is always changing, even when it appears solid and unchanging. Radioactive decay proves this, a spontaneous process in which unstable nuclei transform, releasing energy and particles. In alpha decay, the nucleus ejects 2 protons and 2 neutrons, forming a helium nucleus. This is common in heavy elements like uranium and thorium. In beta decay, a neutron can become a proton, or vice versa, emitting an electron or a positron along with a neutrino. In gamma decay, the composition does not change, but the nucleus releases energy in the form of extremely high-frequency electromagnetic radiation. These processes show that nothing is absolutely stable. And, if this is true for so many elements, why would the proton be immune? That's the question that drives physicists to relentlessly search for signs of its possible disappearance. Physics is built upon principles that, so far, have never been violated at the scales we can observe. Conservation of energy says it cannot be created or destroyed, only transformed. Conservation of linear momentum ensures that, without external forces, a system's total motion remains constant. Conservation of electric charge prevents charges from appearing or disappearing out of nowhere. And conservation of baryon number ensures that the number of protons and neutrons in the universe remains the same, except in processes not yet confirmed. These laws are the foundation of matter stability, but if we discover that the proton decays, we will face a fundamental violation, a clue that there are forces and interactions beyond what we know. So far, every experiment points to the proton being extremely stable. No decay has ever been recorded, even in detectors observing trillions of protons for years on end. Still, in 1967, physicist Andrei Sakharov suggested that the proton might not be eternal. He predicted that, under specific conditions, and over unimaginably long timescales, it could break down into smaller particles. This means that every atom in your body, every molecule in the ocean, every planet and every star would eventually fall apart. In this scenario, the universe would have a silent clock already counting down. Grand unification theories aim to combine three fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. Within these theories, baryon number violation is possible, allowing proton decay. Such decay would release energy and lighter particles, slowly dissolving all matter. Although this prediction is far beyond our current ability to detect directly, it is mathematically consistent. If real, it means the basic structure of the universe is not permanent, and that, one day, everything will transform into diffuse radiation and elementary particles. Experiments like Super Kamiokande in Japan monitor huge volumes of pure water in an attempt to detect the rare event of proton decay. So far, nothing has been observed, but this only pushes the lower limit of its lifespan to even greater numbers, more than 10 to the power of 34 years. If decay exists, it will occur so slowly that it is imperceptible today, but inevitable on cosmic timescales. In that future, white dwarfs and neutron stars, stellar fossils, would break apart, releasing energy and leaving only radiation. Planets and moons would lose their structure, and even the most stable atoms would end up as subatomic fragments. Over time, these bodies may collapse into black holes, which will slowly evaporate via Hawking radiation. The final result will be a dark, silent, and nearly empty universe. Regardless of the proton's fate, one scenario is almost certain: heat death. As time moves forward, energy will spread out, entropy will increase, and the universe will head toward a state of absolute equilibrium. In this state, no significant reactions will be possible. It will be the end of complexity, of light, and even of time as we know it, an eternal silence, sealing the cosmic story. The proton, this discrete particle, may be the universe's clock. If it decays, we will know that matter has a final deadline. If it is eternal, the cosmos will still march toward a silent end. In the infinite stage of space-time, nothing is truly immutable. And if you've made it this far, subscribe to the channel, turn on notifications, and leave your like. This way, you help us keep exploring the universe's secrets, and together, we can travel even deeper into this ocean of mysteries.